Okay, awesome. We figured it out.
Yay.
What is playing in the background?
Something.
Okay. I guess we can just start with question one. If you guys haven't attempted the homework yet, um, I'd say it is difficult, but manageable. Um, yeah, I think I try to make the problem like the first three problems I wrote myself, and I try to make them as like uh timid as possible. So let's start with the first problem.
Wait,
So
is the fraction in the first problem like just k minus I?
yeah, exactly. So if you have what? Wait,
Yes, that's very correct.
how do I say? Uh, there we go. Do I get to write now? No. Um, save to file. Okay, I have pulled up the files. Let's start with the first problem. Oh, yeah, there we go. 1 plus k squared over I plus k. So the nifty thing about complex numbers is that I squared is equal to -1. So that allows us to factor some like very weird quadratics like k squared plus 1, which is namely k minus I times k plus I. And that's basically just a squared minus b squared if b squared was -1 or b equals I. And since we want 1 plus k squared divided by uh, I plus k, then we just have the remaining part of k minus I. So we want the sum of k minus I from k equals 1 to 100. And that is just equal to 100 times 101 over 2 minus 100i. Um, let me see here. It shouldn't. Okay, wait. It shouldn't say the magnitude square because that's a really big number. I have it on my solutions page as just the real part plus the imaginary part. So this is just 5050 minus 100i, and that gives an answer of 4950. And if you're trying to find the magnitude, let me just calculate this really fast. For finding the magnitude, it'd be the huge number of 2551250. And that is it.
This was
Yeah, huh. On my solutions page, it's like 4950. I think when we made like edits to make the problems better, we just only did it on like one document. Alright, let me change this. Okay. Does anyone have any questions? Awesome. Andy, I can do like the first. Actually, do you want to do the second one?
Okay. Number 2. But should I just talk about it? All right.
Yeah, just talk about it.
All right. So, I can't notate. Could you fix that? Okay, so like what I do is I write z as a plus bi, except we know a is 3. So z is equal to 3 plus bi. And so we have 3 plus bi and 3 plus b plus 4i. Right?
Yeah.
And those are the 2 roots. And we also know that it is a cubic. So we talked about how in the ordinal lecture that for every root there's gonna be a conjugate. For every polynomial with real coefficients, if there's a complex root, then a conjugate is also in it. And if the root is real, then the conjugate will be itself, right? So if that means that at least one of z or z plus 4i is real. Wait, is that right, Eric?
Yeah, or the other case where they're conjugates of each other.
Huh? Oh yeah. So each of these 3 cases are pretty simple. So if z is real, that means b equals 0. If z plus 4i is real, that means that b plus 4 is 0 or b is equal to -4. And they're conjugates of each other, then that means that b is equal to -2. Is that right? Yeah.
Yeah, something like that.
And so those are 3 things.
Oh,
And so you just sum them up, right?
It should just be 3.
Yeah. Or something.
The product of roots is constant, so that's how you get the answer for the case for the third root in this case, by the way. For the other cases, you already get all 3 roots. So for this remaining root, to calculate it, we are given that the product of the 3 roots is constant, and the product of these 3 terms is just 75. The product of this is 13, so the remaining root must be 75 over 13. And the remaining root will just be 75 over 13, 3 plus 4i, and 3 minus 4i. And when you add all this together, you get this plus 6, which is 153 over 13. And that is our final answer. Does anyone have any questions? Okay. I can move on to number 3. Number 3 itself is a pretty annoying problem, but since complex rotations are often ugly, I think it's important to still have it there because it's still prominent on contests.
Hey, Eric, I think I've seen this problem before. I have absolutely no clue where it came from.
Math counts?
I did not get to solve it. I did not solve this problem.
Yeah, it was really annoying. I was like stuck between
I'm pretty
Pythagorean
sure this
like
is
complex.
math counts.
Yeah, it's a little bit of
Like
math.
I remember seeing this and like.
Wait, is this exactly the math counts problem?
No, it's similar. Like the problem was like the same format except that A and B were like positive integers or something like that.
It is.
Wait.
And like it asked for
Oh
the
no.
area.
Wait,
It was, like,
this is basically the math
200%.
counts problem. What?
Yeah.
Yeah.
Hey,
Well,
whoever is doing problem is a bad boy.
Wait, my brain
Whoever
was
is
like
making these
spasming when I
problems,
did
actually
this.
reconsider, please.
Well, I kind of like. I think my brain just like broke when I made this. What? That is basically the math counts problem. I guess we'll just show you how to do the number 8 on this year's 2025 chapter math counts. So let's see. First, we can like what I did was I translated this point to the origin. So our 3 points would be 0, 0, a negative b, and like 20, 15 minus b. And now we have that this forms the equilateral triangle. So we either have a minus bi when rotated by e to the wait 1 second. There's like a little typo here. That's just like annoying me. There we go. E to the I pi over 3 is equal to 20 minus 15 minus b. But since we're not given that a, b are positive integers, we have this where a minus bi is rotated by e to the negative I pi over 3. And that is also equal to 20. Wait, why did I write this? We can move them all into a complex form. And now there's really nothing we can do but just the horrible bashing. We substitute e to the I pi over 3 is equal to 1/2 plus root 3 over 2i, and e to the negative I pi over 3 is equal to 1/2 minus root 3 over 2i. And this gives us our answers. I'm not gonna do the horrible messy scratch work out here. But if you have a paper and you like comfortable with like multiplying complex numbers, it shouldn't really be too bad. And you get our final answers of root 3. Root 3 minus 20, 20 root 3 minus 15, and negative 15 minus 20 root 3, and negative 20 minus 15 root 3. And these are just going to be like an ordered pair A, B. And when you add these together, it gives us our final answer of negative 70. I think it could have been a more creative problem, but it is what it is. Does anyone have any questions? Okay. I'll take that silence as a no. And Andy, do you want to do number 4?
Sure, okay. Number 4, it says so we write z, for example, z to 13 is equal to w. So z is equal to w to the 11, which means that z is equal to z to the 143 because 143 is 11 times 13. So that means that z is equal to 0, or like z to 142 is equal to 1. And so that means it's a 142th root of unity has formed 2 pi k over 142, aka pi k over 71. So the answer is 71.
Yeah, when I seen this problem, it was like really weird because I thought it'd be like some really extravagant solution. But since 71 is a prime, it literally can't be anything else. And I think I don't remember what exactly it was. What number was this? It was a number 6, and it has like a 1-minute solution, and that was pretty cool to me. Yeah, that's about it. Anyone have any questions? Okay. For number 5, there is a nice geometric solution, but since we are in a class with complex numbers, I will go over the horrible substituting complex number solution instead. So you could set z as a plus bi, And we get that 75 plus 117 IA plus BI. We want to find the largest possible real part of this. Given that the magnitude of z is equal to 4, so we have 16 is equal to a squared plus b squared. And since we only want the real part, we could ignore the terms that are complex numbers at the end. Sorry, imaginary at the end. So we can just have like 75a minus 117b for this part. And for this part, we can multiply by a minus bi to get 16 over a minus bi 96 plus 144i. And this just becomes 6. This becomes 9. And we have plus 6a plus 9b. So what we really have at the end is 83a minus 108b. I want to find the maximum value of this as a squared plus b squared equals 16. Wait, I might be tripping, but I'm actually like kind of confused now. Andy, do you know what to do? I swear I solved this. I solved this in the AIME. I'm like kind of lost now.
Wait, what?
How do you keep going?
You do the a plus bi trick, right?
Yeah,
And
no,
wait,
you just have this as like a set of equations where you have to maximize this given that a squared plus b squared is 16.
you have something known as Cauchy-Schwarz weight, say.
Wait, but do you have to? Oh, yeah, I guess you would use. Okay, so you just have like 16 by Cauchy-Schwarz, and this is like, oh, our vectors are just gonna be like a, b, and v equals 83 and negative 108. So we have 16 times 83 squared plus 108 squared is greater than or equal to. Wait, do you want the maximum? Yeah, okay, so this works. And we can just like have our value 83a minus 108b squared. And this would wait. And are you sure? Because like this is gonna be even. Oh wait.
You probably made a mistake somewhere else.
Oh, it's minus 108. But wait, but that hasn't changed that. Wait, what? Wait, this is negative. What am I doing? No, wait, it's plus. Wait, I'm actually like trolling. That's wait, I'm very I'm looking wait. Oh my, I just realized what I was doing. I'm looking at this year's like AIME problem, and its answer is an odd number, and I'm really confused. But no, it's like a completely different problem. So I think we are actually okay. So what is 83 squared plus 108 squared? What do I wait? I'm very confused now. Wait, Andy, do you know what is happening?
What do you mean? You solved the problem. There's nothing deep about it.
No, but this isn't a perfect square.
Wait, I know you're selling for.
Yeah,
What
that's
are
probably
you doing, bro?
wait, that's actually probably what's happening.
You,
Wait, was this today? Was this year's AV number 8, or am I like
it was last year's AIME.
it was last year's AV? Oh my god. I thought it was this year's AV for some reason. Oh no. Well, was it AIME 2 then?
No, it was AIME 1. I remember solving this problem.
Oh, good job.
Or is it last year's? It
Oh,
might be.
no.
I don't think it's last year's.
Wait, where did I
We're all so outdated.
I'm actually like tripping, low key. Yeah, it was last year's number 7. Kind of sad actually. Wait, where did I make a mistake though, low key? Kaushi Schwartz.
I'm never letting you
That would be wise. Low key, wait, let me look at this.
Sorry. I'm reading something that's making me laugh.
What is this?
Wait, what is what?
You're supposed to A plus BI it.
Huh? No, I'm
Just
looking at what he's
product?
sending in the chat.
Oh wait, I think I said the wrong thing.
Maybe.
Wrong picture.
Wait, Andy, what do you mean you're supposed to A plus BI it?
Just plug in Z equal A plus BI. Is there like anything else?
Yeah, that's what I did. Where did I mess up?
For 6?
You know what?
No.
Wait, you know what? I'm just gonna restart the problem. Okay, guys. So we
Wait, that's
have
actually so real.
so we plug in A plus BI. And we only want to find the real part. We don't give a read about the imaginary part.
Yeah, exactly.
All right. Wait. And so if we have A plus BI, right? The real part on the 75 plus 117i Z part, that gives 75a minus 117b. On the other hand, for the 96 plus 14i over z, that's equal to 96 times plus 14i times I conjugate, which is a minus bi over 16. And so we can cancel out the 16. So that gives us sure, yeah, 6a plus 9b, right? And so we add them together, we get 81i, Mr. 81a, Mr. Cannot add.
Oh, wait, that's what I was doing. Oh, I forgot how like numbers worked. That's so
All right, so 81a minus 1 over 8i, right? And we want to apply Cauchy scores, so we can like wait, I can all right, whatever. Okay, I assume Eric is confident enough to finish the solution now, and yeah.
Oh wow, it's a perfect square now. Golly gee. And this is just like a 3, 4, 5. Like 27 squared times 3 squared plus 4 squared equals 5 squared. A squared plus b squared is 16. And this is just 4 times 27 times 5, which is 540. Awesome. I think we should like cut the other like 5 minutes out of the recording. That's kind of sad. Wait, is it answer 540? Yes, it is. Okay.
Yes, it is 540.
I solved it, AIME number 7. I'm so good. Okay, wait, yeah. So that's it for problem 5. Does anyone have any questions? No? Okay. I have a lot of questions now. Oh, it's this problem. Annie, do you want to do this? Because I don't think I looked at this like when I was taking the class. I'm definitely not doing that.
Which one?
6.
Oh, hell nah.
Yeah, exactly.
You should not have put this in here.
I'm just very evil. I put a star on it, Andy. Oh, I was lenient. There was a star.
Okay. So if I remember correctly, this was a 2024 AIME 2 problem. Let's see if my memory serves me correct.
Let's see.
It was. My memory is better than yours, Eric.
Wow. Okay, so let's just use the AOP solution because
No, we will not use the AOP solution. We will use the 13th truth of unity.
Yeah, Then not the AF
All
system.
right, so first we can simplify this once the term inside to omega k minus 1 squared and then plus 1.
Wait, hold up. I feel like this would be more helpful if you could annotate.
Mm. All right, so it's gonna
Oh,
be
wait.
omega k minus 1 and then squared and then plus 1.
Wait, what are you saying? Wait, I'm like tripping.
Like it's a perfect square plus 1.
Oh, like that. Okay, yeah, I see what you're saying now.
I have a question about this.
Yeah.
What?
So, like, can we multiply like the values for which k equals 1 and k equals 12, and then do the same for k equals 2, k equals 11, or something like that?
Yes, you could. It wouldn't go far.
Oh no.
How far would it go then?
How far would it go? Yeah, exactly. Yeah, I want to know.
You can try that. That is something left to the reader.
Yeah.
We are short on time because this man cannot add 6 plus 75.
Do not quote that.
Okay, so this and
Yeah,
then we use
proof
difference
quote
of
that,
squares
please.
here. So this is equal to 1 plus I minus w to the k times 1 minus I minus w to the k. The wk has a negative, but like whatever, you can do the other side as well.
Wait, does it matter?
I mean, yeah, I think it does matter.
No, it
It
is like
depends,
this.
but like because the next thing we do is we consider the polynomial x to the 13 minus 1 because we're multiplying this across everything.
Oh, wait, I see what you're saying. Yeah, wait, disregard this. I don't know how like numbers work apparently. There we go.
Okay, after that, we
Let me
have
see if
to,
let me see if I understand the solution. Hold up.
bro, please.
Oh wait, I see how you do it.
You're making my brain sail.
Wait, no, I see how you do this. I see how you do this. Okay, wait, trust. Watch me cook, okay? So since this is we know that omega.
If you sell, you're probably gonna be.
Oh, I mean this is like an AIME so number 13. I should probably
It's a number 13.
Okay, it shouldn't be that bad. So this is a 13 traditional unity. So we have omega to 13 equals 1. Omega 13 minus 1 equals 0. And we can factorize this as omega minus 1, omega squared minus 1, omega cubed minus 1, all the way to omega to the 1, 2, 3, 4, 13 minus 1. Wait, and that is just like wait, stop. Okay, yeah. Oh, all the way to omega 12 minus 1. And that should wait, is that it? And there's also like omega to 13 minus 1. And that just makes it 0. So yeah, okay, yeah, good. Since we know that w is not equal to 1, we can get rid of this. And we know that this is always equal to 0. And since we have like wait, what am I saying? Sorry. Wait, okay, sorry. Okay. We can think of this as a polynomial in terms of x, where x is like omega. And so we just do like x minus the roots of this, which is omega, x minus omega squared, all the way to x minus omega to the 12th. There we go. Did I cook? I think so. Anyway, this should be on track. So when we cycle through this, the product of this, which is the product of these things, we have that we have like negative omega to the 1 plus I, all the way to negative omega to the 12 plus 1 plus I. And that is basically what we're doing here, where we set x is equal to 1 plus I. So we have that this part is just 1 plus I to the 13th minus 1. And the other part is 1 plus 1 minus I to the 13th minus 1. Is this correct? think so. Okay. And now we do some funny observation. And we have that 1 plus I to the fourth is equal to 4 and 1. Wait, sorry, not 4. 4i and 1 minus I to the fourth is equal to 4i. And so we substitute this as wait a minute. Sorry, it's the 6. I can't do like things. Oh, it's equal to 8i. So then we substitute this in. We have 64, negative 64 of 1 plus I minus 1, and negative 64 of 1 minus I minus 1. And we can simplify this as negative 65 minus 64i, and negative 65 plus 64i. And this is just like perfect, difference of squares. And this is the 65 squared plus 64 squared, which is 8,321 for a final answer of 321. There we go. I think that went fairly painless.
Imagine someone actually guessed 321 on the test.
Yeah, just say it's 321, yeah. Honestly, I think like the idea of doing this is actually like very nice. I looked at the solution like before because I remember myself seeing this problem before, and I was very astounded by this, and I still am. So I hopefully you guys can remember this, because this seems like this is like a very
Maybe
useful
it's
technique.
because you didn't learn anything new from the solution.
I mean, yeah, but like I mean I learned it and I forgot. Now I relearned it. Like I remember it better. It's like Yoda, right? You have
And
to
then you're
relearn what.
probably gonna forget it again.
Hopefully not, but it's
Wait,
like
I just realized it's like crazy that I can now I can head solve AIME problems.
you
Such
can
a troll.
solve AIME problems.
Such a
Oh,
troll.
head solve. Oh my god. Wait, which one can you head solve?
All of the I don't know why.
All three?
It's okay, we can just move on.
Oh wow, okay. Wait, you head solve this?
I mean, like, I got the general idea immediately.
Oh, you got that general. Okay, that doesn't count. You have to get a numerical answer.
All right, bro.
Because this is the this is the part that's hard to head solve. Like the idea that you can think
That's
about
also
it.
the easiest part to do anything else. Whatever.
Wait, I don't know. I mean, I guess the concept would be easier, no? Because like you just like think a little, put the squares, and then like, I mean, yeah, if you just have the square use difference of squares, you're basically done. Yeah, because like when you back on track. So the cycle of like omegas, like roots of unities, x minus roots of unities, that's important because you know that this is just equal to x to the 13th minus 1. That is very cool. And you should know that because it is important at contests. We have some fun facts. Publication problems are from real contests. You probably recognize them, but we didn't put them there because you're going to search them on the internet. But it doesn't really matter because we explain most of them anyway. Any questions, comments, concerns, my email. That is all we have for you guys today. Thank you so much for coming. Andy is very oars.
No.
Sorry, guys. Wait, I have some funny.
What?
Wait, let me stop the recording.
No, keep it recording.
No, I'm actually good. How do I stop this?
No. Keep some of the funny parts in it, like.
Oh, this recording is getting absolutely trimmed down. Let me assure you. So you probably won't.
No, keep the part where you actually screwed up. Keep the part where you.
I would edit that out, but I'm also like too lazy, so I probably won't. There we go. Stop recording.